In this video, we are going to be talking about the entry-level unit conversion problems. So this allows, we're going to be converting between kilos, hectas, decas, the base unit, the deci, the centi, and the milli. This is not going to be true dimensional analysis. We are not going to use fractions on this. So we're going to use the saying, King Henry's daughter usually drinks chocolate milk. And what they really mean is this. That's the King Henry saying. And what it allows us to do, it allows us to very easily convert, let's say, a kilogram to a hectogram, to a decagram, to a gram, to a deci, centi, or milligram. So it allows you to convert from any of the gram units that have those particular prefixes. Kilo, hecta, deca, the unit, which is the base unit, deci, centi, milli. An easy way of figuring out where you are on the King Henry chart, believe it or not, is to look at the number of letters in the unit. And for example, if it's a single letter, it's always the base unit, you're always at the U. If it's a double letter and its first one's capital, well, then you're on the left side. If it's a double letter and the first letter's lowercase, well, then you're on the right side. A common mistake students make is they confuse this one with that one. If you notice, the difference is obvious here. When they mean millimeter, there's going to be 2 M's, and when they want you to be at the U, they're just going to give you 1 M. So just be aware of that. Those are the common mistakes. Let me show you how it works, and then that'll be pretty much it. So 500 milliliters. If you want to convert that to liters, here's what you do. First, you have to recognize that in a number like 500, the decimal's at the very end. Then you have to figure out, where is ML on King Henry? Well, it's the M. And where's L? Well, that's the unit. In this case, I have it as a lowercase. It could be uppercase or capitalized. But it doesn't, I'm not really concerned about that. So if we want to go from milliliters to liters, we just figure out, well, I'm here and I want to go here. How many spaces do I have to move? Well, I have to move 1, 2, 3 to the left. Notice I didn't count the one I was starting on. I'm already there. So I need to actually go 3 spaces to the left. So what that means here is we take our decimal and move it 1, 2, 3 spaces to the left. So my answer would be 0.5, or if you wrote in 0.500, I'm not worried about those zeros. That's why I put a line through it. They won't change the value of the number. So what this means is that 500 milliliters is the same amount as 0.5 liters. That's all you do for King Henry. So let's look at the next one. 0.01 centimeters. Well, centimeters is the C in King Henry, and millimeters is the M on King Henry. That's 1 to the right. So I take my decimal and I move it 1 to the right. So my answer would be 0.1 millimeters. The first 0 won't affect the value of the number, so if you don't include it, I'm not worried. That's why I put a line through it. Kilojoules to joules. Well, kilo is the K, joules is the unit. That is, now, keep in mind, you may not know what a joule is yet. It is a type of unit that we use in chemistry, but that's not important. As long as it fits in this King Henry's grid, you can convert from one to the other. So kilojoules the K, joules the unit, that is 3 to the right. So you take the decimal, which is not written in the number, so the assumption is that it's at the end, and we move it 3 to the right. So it's going to be 250,000, decimal there. Again, I don't care if you put the decimal in or not, as long as the number is numerically equivalent, that's all that really matters. We'll do a few more, and then we're done. So kilometers or kilometers to centimeters. That's from the K to the C. That's 1, 2, 3, 4, 5 to the right. So I take my decimal and I go 1, 2, 3, 4. Now I run off the number 5, so I'll have to add an extra 0 in. And there's my decimal now. So 250 centimeters. The zeros in front I don't include. That's pretty standard when writing numbers down. Otherwise you could, in theory, be writing numbers forever. So that's why we don't do that. Now, is there any other, let's see, that are, no, these are all pretty standard. So that's all that I'm going to do. That should explain this. The back of this is going to be for accuracy and precision. That is a kind of a side topic, but I'm going to include it in this video just to make things a little bit easier. They really aren't related, but we'll do them anyway. So accuracy and precision. I like to use a target. And so if this was, let's say I was shooting arrows, and I was really bad. So this would be inaccurate or not accurate, and not precise. In other words, totally random. Now, let's say I was really good at shooting arrows, but my the little thing that I used to line up the arrow and the bow and the target was misaligned. Like this would be like a scope on a gun. I don't know what they call it on a bow and arrow. I'm sure it has a name. But let's say it was a little out of line and it wasn't in the right spot. So I thought I was aiming for the center every time, but I was really going up in this corner every single time. Well, that would be precise. It would be precise because they're all clustered together, but it would be, it's not accurate because the goal is to hit obviously the center. So that would be not accurate, but it is precise. That's very common in scientific instruments, and they typically have to be calibrated to make them precise, okay? Or sorry, to make them accurate. They usually tend to be precise. So let's say I'm really, really good and everything's working great and I hit the target every single time. That would be accurate and precise because they're all hitting where they're supposed to be. Now, in the scientific world, this first one basically means your machine's broken, okay? Because you're getting totally randomized numbers, and that's useless. You throw it out and buy a new one. Obviously, you don't really do that, but that can often be the case. This is what ends up being really common. For example, if you use a pH meter, this is very common. They need to be calibrated in the beginning, so they will be precise, but their pH could be reading wildly off from what they're supposed to be reading. And that's where the calibration comes in, and then this would be something that is calibrated and very accurate. So the definitions I'm going to give are pretty simple definitions. You could look them up and go, Google these and get fancier definitions if you want. But accuracy is how close you are to your target, okay? It could be a target value, it could be an actual target, it doesn't really make a difference. It's how close you are to the actual answer. And precision they are how close the measurements are to one another. So precision just means that they're all clustered together or they're getting the same number. So for example, if I have a weight that I know weighs 100 pounds, I know for a fact it's 100 pounds, and I put it on a scale and the scale keeps reading that it's 110 every time, okay, and I have a bunch of weights and I know they're all 100 pounds and I weigh them on the scale and the scale keeps telling me 110. That would be a very precise scale because the numbers are all close to each other, but it would not be accurate. The way I would make it accurate is to just calibrate it to say, okay, I know this scale is reading 10 pounds too heavy, so if it's a fancy scale, I can just tell the scale to subtract 10 for me every time I put a weight on it. Or if it's not a fancy scale, I can know I'm just going to subtract 10 from it every time. It could be a weight, it could be a length, it could be any measurement you want. Basically, accuracy is how close you are to the correct answer, or your readings are to the correct answer, and precision is how close they are to each other. And that concludes this video.